Not everything in chemistry is black and white. There's a lot of shades of gray in between. We teach the octet rule as though it's black and white. All atoms tend to form chemical bonds so that they can have 8 electrons. Well, there's actually quite a few compounds that deviate from this rule. First of which we're going to quickly cover are free radicals. Free radicals are uncharged molecules. Usually they're very reactive and they don't stick around for very long. And they have an unpaired valence electron. Typically, the types of free radicals that you're going to see are compounds that involve nitrogen. Nitrogen can get by with 7 electrons, and any compound with nitrogen that has an unpaired electron is extremely reactive. So it tends to react with other things to form other more stable compounds. But it's useful just to know what a free radical is, and that nitrogen tends to form these types of compounds. Boron the moron. Poor boron. Boron is an element that achieves stability through only having 3 sets of electrons bonded to it. Boron is stable with 6 valence electrons. And you can actually determine why this is. If you try to make that double bond here with this fluorine, cut that bond in half, look at its formal charge. It has a +1 formal charge on that fluorine. And we know that putting a +1 formal charge on a fluorine is incredibly unfavorable. And that's actually why most halogens form a single bond when forming compounds with boron. So you'll typically see boron in Lewis structures displaying one single bond on each side. And boron is very unique in that sense. Elements that are in periods 3 or below, which means period 3, period 4, period 5, so on and so forth, are allowed to actually expand their octet if they're in the middle of a molecule. The reason why is, as soon as we reach the 3rd energy level on the periodic table, we gain access to the cloverleaf-shaped d orbitals in periods 3 and 4 and so on. Those cloverleaf-shaped orbitals allow elements in periods 3 onward the ability to overlap in new and creative ways in order to achieve expanded octets. So you should just be aware of the fact that, yeah, a lot of elements on the periodic table can form form bonds with more than 8 electrons around them. For phosphate, we know that phosphate is PO4 3-, and its Lewis structure, a valid Lewis structure would be this one here with single bonds around this phosphorus. However, you'll notice that a lot of polyatomic ions actually form different Lewis structures with expanded octets to reduce formal charge. Yeah, this is a decent Lewis structure. Each one of these oxygens have a -1 formal charge, which isn't that bad. But this phosphorus in the middle, as drawn, actually has a +1 formal charge. If we cut these bonds in half, it essentially has 4 electrons around it. It should have 5. So one of those oxygens actually forms a double bond, and this structure will have resonance, because that double bond can move between each one of these other single bonds. And that reduces the overall formal charge. This now has a 0, this has a 0, this has a -1, -1, -1, and all of those formal charges add up to give us the overall charge of the species, which is a -3 charge. We're going to go through some examples of drawing Lewis structures. I think this is going to help us practice the basics and also practice drawing expanded octets. So I would like you to take a decent amount of time, and I'd like you to try to draw each one of these Lewis structures from either the name or the given formula. The Lewis structure for arsenic trifluoride is going to have a lone pair of electrons on the center arsenic. Each of these fluorine atoms is going to be connected with a single bond, and we don't have any deviation from the octet rule. Dichloromethane. Well, you should know that methane is CH4. Dichloro simply just means that we've taken some of those hydrogens and replaced them on the carbon atom. And the carbon atom in the center is going to have all single bonds, and the chlorine atoms have a full octet. Carbon is one of the few atoms on the periodic table that cannot expand its octet. Dinitrogen monoxide. We get a Lewis structure in which we have nitrogen as our central atom, and we should have at least 8 electrons around our oxygen and 8 electrons around our nitrogen as well. You can draw several resonance structures for this molecule. And again, why is nitrogen in the middle? It has the lowest electronegativity, so one of those nitrogen atoms needs to be in the center of this molecule. And oxygen in the middle would not be the most stable conformation of this molecule. This is the most valid Lewis structure because the formal charge on this nitrogen on the left side is a 0. The formal charge on the center needs to be a +1. It doesn't matter which resonance structure we draw. This nitrogen in the middle is inevitably going to have a +1 charge. And we have a -1 formal charge on this oxygen. And that's okay, because oxygen is extremely electronegative, and if necessary, we can maintain that formal charge on the oxygen. Nitrogen monoxide is actually a free radical if it's not a charged species, but this has a +1 overall charge, so that extra paired electron is gone. So when you're drawing a diatomic molecule or polyatomic ion, one of the best ways to do that is to treat one of the atoms like it's your central atom, and then connect the other one as though it's a peripheral atom, and then make your multiple bonds at the end, if necessary. So this would be the triple bonded Lewis structure for nitrogen monoxide with a +1 charge. C2H4, we're starting to get into molecules that have multiple central atoms. You'll notice that 2 carbons that are connected together, neither one of them is really the central atom. It's like they're both a central atom. So the first thing that I did was I connected my skeletal structure, and then I connected everything with single bonds first, and then I noticed that I had 2 extra valence electrons in this structure, and the only place that you could put those valence electrons is between those 2 carbons. That's the only way I can get this Lewis structure to work. Bromates. Initially, if you draw all single bonds around it and have extra pairs of electrons around it, that is a valid Lewis structure. However, the best Lewis structure for bromates is the one that has the most reduction in formal charge. If I only had single bonds around this bromine atom in the center, that would only be 5 electrons. That would be a +2 formal charge on a halogen. That's really bad. So by connecting not just 1, but 2 double bonds, I'm reducing the formal charge of each one of these oxygens and the bromine in the middle. That's a double whammy, 2 for 1 deal. And I end up with a polyatomic ion that has an expanded octet in the center, and that is entirely okay because bromine is in period 4, which means it has access to those cloverleaf-shaped orbitals that can overlap in different ways. It has a -1 overall charge, which matches the formal charge sum of that polyatomic ion. The resonance structures for formates. You'll notice that formates has a overall -1 charge, and it has resonance as well. Something I don't like about these structural formulas is the fact that they're missing the pairs of electrons around these oxygen atoms, and they really should be in the complete Lewis structure. So I want to make sure we're paying attention to that level of detail here. But that double bond is able to move back and forth because of resonance. So there's actually 2 resonance structures for this polyatomic ion. And this actually is a carboxylic acid, right? It just doesn't have the hydrogen attached to it. So it looks very similar to that example that we did in class with carboxylic acids. We have 2 expanded octets for ICl4-1 and xenon difluoride. For iodine bonded to 4 chlorine atoms. Each one of those chlorine atoms would be connected with a single bond, completing their octets. I'm going to have 4 electrons left over that need to go somewhere. And those 4 electrons can just be tacked on to the central atom, and I'm done. That's all I have to do. In the case of xenon, you're going to notice that some compounds can actually form from noble gases, more particularly xenon and sometimes krypton. If you have very large atomic radius, noble gases, those outer shells can actually accommodate some very weak covalent bonds. So xenon difluoride, you'll have a single bond between the fluorine atoms and the xenon atom itself. And sometimes you'll see that you can draw those extra pairs of electrons with perspective-based drawing just to show that they're oriented in different directions around the xenon atom, and that's fine too. For our next mini lecture, we're going to cover valence shell electron pair repulsion theory, and we're going to get back into molecular shapes.